Welcome to the Proton Guru video practice for topic 4.3. These problems will give you practice on Diels Alder reactions. Some brief and straightforward reading to get you ready for these kinds of problems can be found in the Organic Chemistry 2 Primer 2019 by Dr. Houjeiry and co-worker. And you can find additional videos and the way to match those videos up to your course textbook at protonguru.com. We'll start off with a simple Diels Alder problem where you are asked to provide the major product of the reaction shown. In this case, it is useful to think about the general mechanism for a Diels Alder reaction first. The Diels Alder reaction in its most simple form will yield a cyclohexene, and you're trying to identify a diene as one of the reactants and a dienophile, which is something with a pi bond, as the other reactant. Here it's relatively easy to pick out the diene, and shown in red, and the dienophile then is the compound with one alkene unit in it, which is shown in blue. If you then look at the general mechanism and the general form of the product, you simply have to fill in the substituents that are in the reactants that are not in the general mechanism. Not every reactant for a Diels Alder reaction has these nitrile groups on them. And if we do that, we will make a cyclohexene like this, where carbons 5 and 6 in the starting material are the ones that have the nitrile or CN functional groups on them. Now you'll also notice that in the product I've drawn the two CN functional groups being trans to one another. That is because the Diels Alder reaction is concerted, which means there's no rearrangement of this trans alkene where the two CN groups are pointed opposite directions. So in the product they should be trans to one another as well. Another really important point is you have chiral centers here, and there is not a plane of symmetry in the molecule, so this is a chiral molecule. And neither of your starting materials were chiral. Anytime you produce a chiral product from achiral starting materials, you would expect to get both of the possible enantiomers in equal yields, and that is the definition of a racemic mixture. Here's another question asking us to figure out the major product, and this illustrates the fact that it's not only alkenes that can serve the role of dienophiles, you just need something with a pi bond. So in this case, we're going to use an alkyne. If you think about the general mechanism for the Diels Alder reaction, and then extend that to changing your alkene to an alkyne, the only real difference is that although we do use one of the pi bonds, since we started with two pi bonds over here in the alkyne starting material, we will have one of the pi bonds left in the product. We have to keep that in mind as we try to figure out the correct mechanism. And we start off by thinking about numbering the carbons in the diene and the dienophile so that we can position substituents accordingly. And in the product we get the double bond between carbons 3 and 2, which is here, just like in the general mechanism. Carbons 5 and 6, you've used one of the pi bonds. This arrow shows that pi bond pair of electrons being donated to carbon 4 to make this bond. And then carbons 5 and 6 in the starting material also have this ester functional group on them. So we have to put those, and I've drawn them in abbreviated form here, but all those functional groups have to be present. And unlike in the previous case where I had some trans cyano groups, here these are sp2 hybridized carbons, which are trigonal planar in their geometry. So we don't have any wedges or hash lines to indicate these pointing towards us or away from us. These should be planar, and this is a symmetric molecule. There are no chiral centers, so we don't need to think about the possibility for other isomers. And that's our final product. Another kind of common Diels Alder reaction problem is one where you are shown a particular product and asked which starting materials you would need to prepare that indicated product. And again, it's always instructive to jot down the general Diels Alder mechanism and figure out where the different pieces come. The diene will always provide you with the unit where there's a double bond formed between carbons 3 and 2. So if you can identify that piece in the target and say, well, this is the double bond that I have, and in my simplest general mechanism I know that that double bond is between carbons 3 and 2, which came from the diene, then I already can pick out which carbons came from the diene. And then the dienophile must be the other piece. So if I think about the two pieces that must go together to form this particular product, I would select this diene, carbons 1 through 4, and that's the same as in the general mechanism here. They will comprise this piece of the product, which in our particular case is this piece. Carbons 5 and 6 have these aldehyde functional groups, the COH group. Now, since they are cis to one another in the product, they must be cis to each other in the starting material as well. So only these two particular starting materials will yield the target product. One of the more challenging types of questions for a lot of students who are first studying the Diels Alder reaction are reactions in which one of the starting materials or both are cyclic. So here's a question involving a cyclic starting material and an acyclic starting material, and it's asking us which is the major product of this reaction. Again, we think about the general Diels Alder mechanism, and we pick out in the starting materials where's our diene. That's usually pretty easy to figure out because it's got to be two pi conjugated alkene units right next to each other like that. And then we figure out, well, what's the dienophile unit? It's got to be a pi bond here. And those will go together to form a cyclohexene type structure. And after we figure that part out, we need to decorate this cyclohexene with the correct other units. We're going to have, for example, an oxygen that links carbons 1 and 4. So if we're thinking about that, we say, well, in our particular case, carbon 1 and 4 are linked by an O group, as I show over here. And then on carbon 6, we're going to have this ester unit. So we might think, well, according to our general mechanism, we'll form this cyclohexene, and carbon 6 happens to have a substituent. So our product should look something like that. Now, in positioning this substituent, we could have placed the substituent as we initially drew, pointed down with this group pointed up. So in this case, we have the double bond that was formed between carbons 2 and 3 in the plane of the page, and we have this pointed away, whereas the other group points towards us. Now, we could have just as well drawn the substituent pointing towards us here, as well as this group at the top. Remember that when you have an electron withdrawing substituent on your dienophile like this, you want it to point the opposite direction of this group and point down towards the page in the same direction as the double bond. So we will just consider the endo product going forward in this problem. And if we jot that down as a potential product, it would look like this. Now, anytime you make a product and you start to see chiral centers, you have to think about the fact that, well, neither of my starting materials are chiral, but my product is, so I will have to get a racemic mixture of the two enantiomers, where I've just changed the wedges to hash lines and the hash to a wedge in these two cases. One other point I'd like to make on this particular problem is that there are a couple different ways to draw this type of bicyclic structure. I drew it this way in our initial discussion. A more common way for a chemist to draw this structure would be to draw the six-membered ring sort of like this. This better represents the real geometry, but we've shown in this representation the O going one way, and here it's up, and this group going down. And this just shows you a different way that one could represent the structure. This is especially important for you to realize that these two are the same thing when you think about doing multiple choice tests like standardized exams. If you know on your scratch paper the answer should look like this, but the answer choices are drawn out more like this, well, you'll have to be able to recognize that those are two different ways to represent the same thing. So here I've drawn this bicyclic structure in a similar fashion to what I did for the previous problem, but I'm asking this in the opposite direction. Instead of asking you what the product will be, I'm asking you to provide the starting materials that would get you to this product. One thing you'll notice right away differentiates this problem from the previous one is that you have two double bonds. So if you think about the general Diels Alder reaction, you would need to have two pi bonds in your dienophile so that one of them remains in the product. We saw that a few slides ago for an example with an alkyne reacting with a diene to make the cyclohexadiene. And when you are asked to provide the reagents, in this case, it provides you with a bit of a problem. Because there are two pi bonds, either of the two sides could have been provided by the alkyne. So we actually have two choices of which side came originally from the alkyne and which side originally came from the diene. So let's think about both of those cases. We could start with this compound, and if we did that, carbons 1 and 4 in the product, right here and here, would be joined with this oxygen, just like in the starting material. And then carbons 5 and 6 would have these functional groups on them as substituents. So that would work. That would be a reaction that would give us the correct product. But we could also make the target product as shown down here. We could have just acetylene providing carbons 5 and 6 on this side, in which case it would be carbons 4 and 1 that were joined by the oxygen, as shown here, and that would match up in our product. So that would also make sense. And then in that case, carbons 3 and 2 would be the ones that have these particular functional groups on them. So there are really two potential ways that we could make the same product. And the trick to getting this question right would be to notice the wording in the question. It says which reagents are needed to most efficiently produce the indicated product by a Diels Alder reaction. Well, in a Diels Alder reaction, if your dienophile has electron withdrawing substituents, if we draw out the substituent, we can see that there's a polar oxygen-carbon bond and a partial positive charge on the carbon in that unit. That means that this dienophile has electron withdrawing substituents on them. And we know that an electron withdrawing dienophile increases the reaction efficiency, so we would want to use this dienophile rather than just acetylene. So this is the most efficient combination of two starting materials we could use to access this particular target product. And finally, we have to address a case where both of our starting materials are cyclic, and we're asked here, what is the major product of this reaction? Again, we have to think very methodically and think about the general Diels Alder mechanism first. And if we do that, we should be able to identify the diene. That's pretty easy to pick out. Even though it's in a cyclic structure, it has to be two alkenes pi conjugated with one another. And I've numbered them 1, 2, 3, 4 to indicate how those will manifest in the product. And if we look at the other compound, we see an alkene in that unit. That must be the unit that serves the role of carbons 5 and 6 in our general mechanism. Having now identified the diene and dienophile, we can think about what the product should look like. If we make our initial cyclohexene ring like this and number it 1, 2, 3, 4, 5, 6, carbons 5 and 6 should be linked by this unit, and that unit is an anhydride. So we take carbons 5 and 6 in our product and link them with that unit. And carbons 1 and 4 are linked by this ethylene unit, and that would be right here. And although there are chiral atoms here, 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 and here in this structure, we also see that there is a plane of symmetry. So this is a meso compound, a compound with chiral atoms, but the molecule has its own symmetry. So there's only one possible isomer to draw here. Now, you may see the same product drawn like this, where the double bond is between carbons 3 and 2. Carbons 1 and 4 are linked by this ethylene linker. Carbons 6 and 5 are linked by this anhydride unit. We can see that these two are the same product, just drawn in different ways.